Hello and welcome to a video on exponential functions. The goal of this video is to introduce the idea of exponential functions and compare and contrast it a little bit with linear functions. So you can see in this graph here we have both an exponential curve and a linear curve. And one of the things you might notice about this is that they start out very similar. In fact, you can't really tell the difference looking at the x-axis points 1 and 2, but once you start to get past 3, then the exponential takes off and it's eventually much higher, much greater of an output than the linear function. And I like this quote by Ray Kurzweil, who wrote one of my favorite books in 2006 called The Singularity is Near. He talks a lot about exponential growth. Says it's seductive, starting out slowly and virtually unnoticeably, but beyond the knee of the curve, it turns explosive and profoundly transformational. And that's basically what's happening with technology, and that's the thesis of his 2006 book. Okay, so let's talk about a formal definition of what an exponential function is. Okay, so an exponential function is the function of the form f of x equals some constant c times some growth factor a to the x. And x can be any real number. In fact, let's break all of these down. C is called it's the initial value. A is called the growth rate. And x is the independent variable. Independent variable. Okay, now the independent variable can be any real number. Okay, the initial value is anything but 0. Or else you wouldn't have a function there, right? It'd just be 0. And the growth rate has a couple of restrictions because if you think about it, you really don't want to be, you don't want a to be 1, because if you raise 1 to some power, nothing's going to happen to it. So that's one of the restrictions. A cannot be 1. And also we don't want a to be negative, because if the base is negative, it's going to kind of it's going to mess things up when the variable goes from an even to an odd number. So if you have a negative base and you raise it to the second power, it's positive. You raise it to the third power, it's negative again. And that's just going to, that's not what an exponential curve looks like at all. Not switching signs like that. It's a smooth curve. So we also want to say that a has to be greater than 0. So there's basically two places that a can be. It can be between 0 and 1, or it can be greater than 1. And those are going to be the two different kinds of exponential curves. Now the theorem I'm going to show you is a definition for how to find a. A is the growth rate. It's kind of like goes side by side with the slope for a linear function. And we have a formula for the slope, and this is going to be the formula for the growth rate. And basically what it is it's f of x plus 1 divided by f of x. That means that we're talking about consecutive inputs. So if one of the inputs is x, the next input would be x plus 1. So these are consecutive inputs, and this will equal the growth factor. So that's a. And this, another way of saying this is the ratio of consecutive terms. Ratio of consecutive terms. And another way of saying this sentence right here, f of x plus 1 over f of x equals a, is to say that a term is equal to the growth factor times the previous term. So in other words, we'll say it like this. We'll say f of x plus 1, any term, is equal to a times f of x. And you can see that in the definition here, because if you just multiply both sides by f of x right there, that's where we get that. Okay, so let's take a look now at a comparison of some things, some features of linear and exponential functions. Okay, so our general form for a linear function, we have one, right? Y equals mx plus b, or we could say f of x equals mx plus b, where we know the slope and the y-intercept from there. And with the exponential, the counterpart is f of x equals c a to the x, where, again, we know that a is called the growth factor and c is the initial value. Okay, now this sentence right here, consecutive outputs, this is a slope formula kind of in disguise. If you think about this formula, the inputs are x plus 1 and x. So it's kind of like saying the general slope formula only with consecutive terms. If you put this into the slope formula, just kind of work off to the side here, we would have f of x plus 1 minus f of x over the difference in the inputs, which would be x plus 1 minus x. That's still 1. That's where the 1 comes from over here. Okay? So that's where this 1 comes from right there. All right, and we have the consecutive outputs to get the growth factor is a quotient for exponentials. All right, so they're subtracted for linear functions, they're divided for exponential functions. All right, another way of saying that, there's a constant difference in outputs for any two consecutive inputs if it's linear, while there's a constant ratio of outputs for any two consecutive inputs if it's exponential. And we can say that the average rate of change is also constant. It is the same thing as the slope for a linear function, but that's not true for an exponential function. In fact, the average rate of change is never really the same for any consecutive points. You can find 2 points that have the same average, but the rate of change or the slope is constantly changing in an exponential. If it's exponential growth, the slope is constantly increasing. If it's exponential decay, the slope is constantly decreasing. Okay, so let's just look at one type of problem here to be able to determine from a table, and the table is given consecutive inputs. So if you look at all of these tables, these are the inputs, and they're consecutive, right? There's no skipped values, -1, 0, 1, 2, 3. There's no skipped values for any of the inputs for any of these tables. So we're just going to focus on that output thing, and by thing, I mean if the difference in the outputs is going to be the same throughout, then we know we're looking at a linear function. And if the quotient of the outputs is the same, consecutive outputs, then we know we're looking at an exponential function. So let's look at the outputs. Let's look at this first example. We'll just we'll be in the habit of checking the differences first. So the differences would be 2 minus 5, and then -1 minus 2, and then -4 minus -1, and then -7 minus -4. And this one is -3, -3, -3. This is a constant difference. So this does have a constant difference. Now given that, and also given this very valuable point there, that is the y-intercept when x equals 0, we're able to write the equation, slope-intercept form. So we can just write here f of x equals mx plus b. We found the rate of change to be -3, and that's going to be x, and we know from right here that the y-intercept is 2. So this is linear, and there's the equation. All right, let's look at the next example, see what we get. So we'll try linear. So looking at this, I would do the same thing. I would do 16 minus 32, 8 minus 16, 4 minus 8, and they're all different, right? -16, this one is -8, this one is -4, so they're not the same. So let's try to look at the ratios. So we have 16 over 32, we have 8 over 16, 4 over 8, and 2 over 4. And they're all equal to 1/2. So here I should have said, maybe we should have said here m is -3. This time a is 1/2. So we found our growth rate. We've also found our initial value as 16. That's our c. That's going back to the definition. C is our initial value right here. We found our growth rate and we have our variable. So we have all that we need to write the exponential function. So we've got f of x equals the initial value of 16 that's when x is 0, times 1/2 to the x. And that is our exponential function. Let's look at the next one. So let's first look at the differences. Whoops. So we would go 4 minus 2, 7 minus 4, and they're already different, right? So it's not linear. Then we try the ratios. We go 4 divided by 2, 7 divided by 4. This is 2, and this doesn't reduce at all. It's, well, you could call it 1 3/4. So it's not, these are different, so it's not exponential. And so we can't really write an equation for this, so just say neither. Okay, hope you found this video helpful.